Today's lecture is the last chapter, chapter 13 on X-ray production. So we learn from the book that if we think about a conventional X-ray tube, it's actually a particle accelerator. And we've seen this before, that if we take electrons and we accelerate them and we smash them into matter, that there's two possible routes by which X-rays can be produced. One of them is, of course, is Bremsstrahlung, and you'll recall that in Bremsstrahlung, if we have an atom and we've got electrons surrounding the atom, and then we've got an electron that's actually coming in here, as it approaches the vicinity of the atom and the nucleus, it actually slows down, and this braking, the energy that is actually lost in braking as it's moving around the nucleus, actually is given off in the form of an X-ray photon. So that's Bremsstrahlung. And again, you'll remember that Bremsstrahlung, which I'm probably not spelling correctly, I think there's two S's, something like that, and I think there's probably an H in here somewhere, Bremsstrahlung. But these X-rays are continuous. Unlike the other form of X-ray that we have, which would actually be if we had electrons out here and we came in with an electron that was sufficiently energetic that it actually caused this electron, it actually hit this electron and knocked it, maybe I should show this at a different angle, it actually knocked it out of its orbital. So the electron is ejected. Then we have, that would be an inner shell electron. So we have other electrons outside of that. And of course, what then happens is we have a hole here. So one of the other electrons is going to fall into the hole, and as it does, it will emit a characteristic X-ray. So the characteristic X-rays are the ones that actually have discrete quantized energy levels. And so those are the two kinds of X-rays that we have. And the way that X-rays are actually made, and I'll probably do right after this, it won't be required that you actually watch it, but I'm going to have probably make a little short video actually demonstrating to you how X-rays are produced, because I've got a couple devices here that are cathode ray tubes that actually will produce X-rays, and I wanted to show you that with a Geiger counter. So what we do, if we want to actually make X-rays that are going to be used, and the purpose of these would be, I'm not really referring so much to the X-rays that are used in diagnostics, but these are really the X-rays that are used in treating neoplasms and treating cancers. So the kind of X-rays that we use there are going to involve fairly high voltages, and we need a filament. So we're going to have some kind of a filament here that's going to be our cathode. This is the negatively charged part of this. And then there's going to be an anode, and the anode is usually actually set off at an angle here, so that electrons are going to come in. See if I can show you this the way that I'd like to show you. So electrons will actually boil off of the cathode, and they'll go to this positively charged anode. So, whoops, there we go. So they're going to strike the anode, and this will have, there'll be a certain angle here from the vertical. If we look at that angle there, we'll actually find that we call this A. That would actually be the length of the. This is actually the length of the anode, and this lowercase a is actually the length of once X-rays are going to be produced. They're going to be produced. Whatever this length is here, this is going to be a smaller length. It's going to be given by the sign. It's actually going to be a sine. Little a is going to be a sine of theta. This is the angle theta here. So if we, for instance, adjust that angle to 30 degrees, the sine of 30 degrees. Oh, by the way, for those of you, I realize that maybe not everybody has had trigonometry, but let me just define what a sine is. If this is the angle, theta, and this is a right triangle here, the sine of theta, it's written S-I-N, it's actually spelled S-I-N-E, but the symbol is S-I-N. The sine of the angle theta, Greek letter theta, is going to be equal to, this is x, this is y, and I'll call that r. It's going to be y divided by r. So y, which is actually a here, is equal to r, which is the capital A, sine of theta. And that's telling us basically that if this length, whatever this length is here, this length now is going to be 1/2 of that. So it's actually showing us that when the electrons boil off here and we allow them to hit at an angle, they're going to have a tendency to reflect at an angle, whatever the angle theta is here, and we're actually going to get X-ray production in this direction. So we do get some reflectance, and there's a couple definitions that are given in your book. One is the filament current. That is actually the amount of amperage that is placed on this filament, and it's usually several amps. And then there's also what's known as the tube current, and this is the current flowing inside the tube, which is made up of these relatively few electrons that are actually moving across here, and that's usually a couple tenths of an amp. The focal spot is the place on the target where the electrons actually hit the target. So we have a target somewhere along here where the electrons are actually going to strike the target. And as I said, we're going to get some bremsstrahlung production, and we're also going to get characteristic X-rays, the energies of which are going to be determined by what shell they're ejected from and the specific atom or element that's actually involved. And we use, because of the fact that this is heated to a very high temperature, we use tungsten as the filament. It's got the highest melting point, I believe, of any element. Okay, so in terms of the X-rays themselves, higher energy X-rays are more penetrating than the lower energy ones. They're less likely to interact with matter, and therefore they're going to actually go further into tissues. So if we actually look at the X-ray spectrum of which is found on page 315, I'm sorry, 215, we can look at the number of photons that are produced versus photon energy. Let me erase this. And you can see that there is a direct correlation between these two, but it varies as we actually increase the photon energy. So if we have number of photons on the y-axis, and we have the photon energy on the x-axis, we'll find that we're eventually going to get to the chart says tube voltage, but it's probably it really refers to the current at that particular point, but the photon energy is down here, and it goes from some level. If we start up here, and if we didn't have any, if there was no inherent filtration, this is actually due to the fact that the X-ray tube itself, it's made of a certain kind of material. The type of the enclosure, the type of material this is made out of, the type of coolant that's actually used in here, because we have to cool this thing down, and further the type of exit window and the structure of the exit window through which the X-rays are going to be emanating. All of these things are going to contribute to something called inherent filtration. So if there were no inherent infiltration, we'd see a relationship that would look something like that. And that goes right down to the point where we actually hit the tube voltage or current. In actuality, that's not what we see. We actually see something that looks like this. And this very, very broad hump that we get here is something that you'll probably recognize as bremsstrahlung. Remember, it's a continuous type of radiation. But then we'll get some sharp peaks, which are characteristic peaks. So we get a couple of those, and then finally it falls off. It actually falls off faster than I'm showing it here. It's actually below that line, so it's kind of falling off like that. And then these peaks would be coming up from here. We still have this dotted line going across like that. So you can see how you are getting bremsstrahlung. You're also getting your characteristic X-rays. As the current increases, the beam intensity increases. So as we apply more current, and when we're dealing with electricity, we've got the terms current and voltage. And voltage, I can show this more by an analogy. If we look at, think of water in a fire hydrant, for instance. There's a lot of pressure in a fire hydrant, a lot of pressure on the water. If the water isn't flowing, there's still a lot of pressure on the water. But until we actually open up the valve on the fire hydrant and we actually get some flow of water, we have no current. Well, electricity is kind of like that. If you think of the flow of electrons as being the current, which is measured in amperes or amps, the actual term is amperes, but they're called amps. The pressure that's actually on this is the voltage. So this is the current, and the pressure, if you want to call it that, it's not really pressure in the normal sense, but using the water analogy, is actually the voltage. So we can have a lot of voltage, but if we don't have flow, if we don't have a lot of flow because we have a very high resistance, we're not going to see a lot of current. Okay, so I just wanted to clear that up. So as the current, the amperes increase, we actually see an increase in the beam intensity. But as the voltage increases, as the pressure increases, that's going to actually cause the average photon energy to increase. So I can show you this in another way, which is not in your book, and that is if we think in terms of electromagnetic radiation, which of course X-rays are a form of electromagnetic radiation, and these things are propagating in a sine wave. So I might have shown this before. I don't remember whether I did or not, but we'll have some 0 point here, and then they'll be equally spaced above and below this. We'll have peaks and troughs in here. So when we talk about, for instance, when we're talking about current, an increase in current, that's giving us an increase in the amplitude, which is the height of this. It's kind of, if this were light, we would call this brightness. But for X-rays, it's actually the intensity of the X-ray beam, increasing the current. But it's not actually changing photon energy. Now, changing photon energy, what that's going to do is that's going to cause a change in the frequency. That is the number of these waves that we get in a particular point, in a particular period of time, if this is time here. So we're actually getting an increased energy if we get more waves per unit time. So that's the relationship between voltage and current as applied to an electron beam. And on the next page, well, I've already given you this to try to show you this little diagram that shows you the small a. It's figure 13.3, which shows the geometric reduction of the beam size relative to the focal spot size. So you have the beam hitting the anode and then a smaller beam actually coming out of that. And that's known as geometric reduction. Low energy X-rays, as I said before, are good for treating surface tumors. For instance, certain kinds of skin cancer, like melanoma, respond fairly well to low energy X-rays. But and these would probably be in the 5 to 15 kilovolt range. If we go up to 50 to 150 kilovolts, then we can penetrate about 5 millimeters, which is about 1/5 of an inch below the surface of the skin. So we can get something that's a little bit deeper. And you know, by increasing the voltage, we're going to get ever increasing depth in terms of our penetration. At less than 1 millivolt, X-rays actually have a tendency to reflect 90 degrees from the electron beam. So these lower energy ones are the ones that actually they're the ones that are going to be more reflective. They're going to actually hit this, and they're going to tend to reflect at a right angle. Not entirely, but for higher energies above 1 MeV and above, then X-rays are going to hit something, and they're just going to kind of pass right through. We're going to get, instead of reflectance, this would be reflectance. What we would actually see in the case of a higher energy beam would be transmission. That is where this entirely passes through whatever our target happens to be. Okay, let's see, what else do we have? So you can see on page 217, there's a little diagram of a transmission target, and you know, basically it's just a little disc that's put in here, and again, if we're more than 1 MeV, the electrons that strike this are actually going to produce X-rays. So the electrons are coming in here, and when they actually strike this, they're going to produce X-rays, and the X-rays will continue along this direction. You know, for the lower energy beams, they would tend to reflect. The X-rays that are being produced would actually tend to reflect at a right angle. They would reflect downward or upward. Okay, only a small part of the projectile's kinetic energy actually goes into production of X-rays. So we've got a couple things here. The fraction of electron energy that is converted into X-rays is given by we call that F, and F is actually a function of both the electron energy in MeVs, in million electron volts, for the energies for the electrons that are going to be actually boiling off of the filament, and the other part of that is actually the atomic number of the element, that is the target element. So for instance, if we're actually, well, it's not the target, it's actually the anode, whatever the anode is composed of. Since the anode is usually, as I say, we're usually, at least for these high energy ones, we're usually using a tungsten filament. Tungsten has an atomic number of 74, and the relationship is F is equal to 3.5 times 10 to the minus 4th Z times E. So Z being the atomic number and E being the energy in MeVs. So for instance, here we have an example that's given in your book. It says if we have a tungsten anode and the tube potential is 140 keV, which actually becomes 0.14 MeV, and then we multiply that by 74, we'll get a value of 0.0036, which corresponds to only 0.36% of the energy, of the electron energy that is actually converted into photon energy. So you can see that that's quite small. The way, of course, we can increase it increase that function is to increase the voltage here. That would be one way of doing it. And the other way is, I suppose, is that we could use a higher Z target. But cranking up the voltage is probably the easiest way to actually get more photons, more X-ray photons. Okay.